Ah, chapter 3. You're like the old school Willy Wonka everlasting gobstopper. You just never quite seem to end. Um, and so here we are again with the endless chapter 3. We are now going to take two of the main ideas we've talked about recently. We're going to take this idea of mean, we're going to take this idea of standard deviation, and we're going to talk about how we can combine these two quantities in a really powerful way. We're going to talk about how we can combine the mean and standard deviation to get a measurement that really tells us the value, the worth, the remarkableness or lack thereof of a particular observation. Something we'll see that's called a z-score, and it's kind of what we're going to work up to in the next couple PowerPoints. Now, I will say the material we're working on now, it involves a lot of pictures. I did my best with these pictures. You'll see they're very, very crude, borderline embarrassing in this PowerPoint, but you'll see I figured out something a little bit better, I think, in the next PowerPoint. Um, it's one of those things where I think doing it in an online environment is more difficult, more challenging than if we were sitting in a classroom together. On a whiteboard, I can erase things, I could point to things, right? I could create these dynamic pictures instead of these sort of individual snapshots that we're forced to deal with in a PowerPoint. I do encourage you to really stick with this material. I do encourage you to engage with it. Don't just kind of gloss over it. It is important that you really sort of get this stuff burned into your brain's muscle memory. It's very picture oriented, which means that maybe visual learners pick it up quickly. But of course, not everyone's a visual learner. Some students pick it up a little more slowly than others. That said, I do think that I've never come across a student who couldn't pick it up, just if they put a little extra time. And despite the fact that sometimes it takes that extra time, one nice thing about the material that we're going to talk about in this PowerPoint as well as the next PowerPoint is that this material is very, very, very amenable to drilling and doing homework problems. So make sure that in addition, even if you feel like you understand what we're doing in this PowerPoint, it's easy when I'm walking you through it. Really make sure you sit down and do as many problems as you can from the textbook. Just do them over and over and over. Repeat them and repeat them and repeat them. Do it until you're feeling sick into your stomach, till you're nauseous, till you're ready to vomit, and then just keep going just a little bit more, okay? That it will be painful in the moment, but it will have a nice payoff as you move through the rest of this course. All right, so with with that legalese, with that legal disclaimer behind us, let's go ahead and plunge forward. All right, just a little preliminary before we get started. We're changing perspective a little bit, right? We talked about the mean previous, but really, right, we made this distinction. It was really the sample mean. Remember, we abbreviated it X bar. We talked about the standard deviation, but again, it was the sample standard deviation. We abbreviated it S. That is, much of our previous work in this chapter has been focused on these sample quantities. Now, if we think back to that very, very beginning, right, of this class, we started by talking about this distinction of population and sample, right? We said the sort of big picture statistical problem, the big picture research problem is that we're interested in a population. We're interested in some characteristic, some quality of the population. However, the population is just too vast for us to look at in its entirety. So what do? We settle. We settle for taking a sample, and we use that information in our sample to infer, to come up with some good guess about whatever it is we're interested in the population. We can be a little bit more explicit now, right? So what might we be interested in the population? Well, here's two possibilities. We might be interested, for example, in the mean of a population. In this case, we abbreviate that with the Greek letter mu. That's that symbol that looks kind of like the letter U. It's a Greek letter mu. That is, the sample mean X bar is a best guess for the population mu. Again, if we were interested, for example, in the average salary of all nurses, there's no way we have nearly enough time. I know I'm way too busy to track down every single nurse throughout the entire country, figure out what his or her salary is, add up all those millions upon millions of salaries and divide by however many numbers there were, right? In theory, that quantity exists. In theory, it could be done. In practice, it's not realistic. And despite the fact that that's what we want, right, we settle for taking a sample of maybe 50, maybe 100, maybe 200 nurses. We look at the average, the sample mean, the mean of that sample, and we'll see that becomes our best guess for the population mean. Now, how good of a best guess is it? That's a more difficult, a more interesting discussion that's going to come down the road. But for now, hopefully we can just settle on the hopefully intuitive idea that the sample mean is a good guess for the population mean. Similarly, the sample standard deviation S is our best guess for the population standard deviation, which we abbreviate with the Greek letter sigma. And for now, for sort of the remainder of this chapter, for the next two PowerPoints, we're going to kind of change focus a little bit, and we're going to sort of talk about populations. And since we're talking about populations, we're going to be talking about population means mu and population standard deviations sigma.
Now, these things particularly come into play based on something called the empirical rule. And it turns out that for a symmetric mound-shaped histogram, or for a population from which if you sampled from it and drew a histogram, you would expect to see a symmetric mound, sometimes called bell-shaped histogram, the following facts are, there's a little bit of rounding here, so the following facts are roughly true. 68% of all data values, 68% essentially of our population, fall within one standard deviation of the mean. 95% of all data values, or 95% of a population, will fall within two standard deviations of the mean. And virtually all, although not quite, 99.7% of all observations are within three standard deviations of the mean. Now keep in mind, right, when we're talking about this histogram, we're sort of talking about this idea where the total area under the curve, remember this will be an important fact later, the total area under the curve is 100%. It's 100% of the area. Graphically, this is what we're talking about. So these facts are actually facts related to the population. So this is my symmetric mound-shaped histogram. Now I know a histogram we've talked about has a bunch of bars on it. So imagine, right, that this is just sort of like a smooth curve drawn over the bars. So you can imagine a symmetric set of bars creating a histogram that would have this nice bell shape to it. Now, mu is the center, so for a symmetric mound shape, for a symmetric bell-shaped distribution, sometimes this thing that we're looking at is called a bell curve. The center of it, the peak of that bell, will always be at the mean. So there's that Greek letter mu right at the peak. Now sort of focus on the bottom. The bottom says that if we go one standard deviation out to either direction, right? To the right, it's the mean plus a standard deviation. To the left, it's the mean minus one standard deviation. This is that blue area, and that's 68%. If you go further out, the mean plus two standard deviations and the mean minus two standard deviations, if you look along the bottom, it tells you that total area, which is the blue plus the red. That collective area is 95%. And then if you go to the very bottommost number, right, it stretches out the farthest. It goes from the mean plus 3 standard deviations to the mean minus 3 standard deviations. That essentially is 99.7%, which means that it's not everything. It means that those tails still trickle off and still have a little bit of area left in them. In fact, mathematically, those tails trickle off for infinity. Right? They go on and on and on and never quite end, although they get closer and closer and closer, arbitrarily close to sort of zero, to sort of closing off. Now, if you look on the top, it kind of breaks that area up into a couple different pieces, which is sometimes useful to be able to have. For example, that middle blue part, from a mean plus a standard deviation to a mean minus a standard deviation, that entire blue area is 68%. Because of that symmetry, we can say that the area to the right of the mean, to the right of mu, to the right of the peak, between it and mu plus sigma, we could say that area is 34%. What's 34%? It's half of that 68%. Right? So even though we really only have three numbers, that's 68, 95, 99.7, you can see by looking up above, we could sort of chop or dice those areas into a whole bunch of different numbers. So let's look at an example on how we might explore these types of problems. So let's say that we know SAT scores are known to have a symmetric mound-shaped histogram with a mean of 1500, so that's our mu, and a standard deviation. Here I'm talking about the population standard deviation, so a sigma of 300. Now we're going to walk through. We're going to look at like 4 or 5 different questions. We're going to answer them one at a time. The first question is this: what percent of students score between 1200 and 1800? So when I say it has a symmetric mound-shaped histogram, I'm basically saying that if I sampled all the students from our high school and I recorded all their SAT scores and I made a histogram, the histogram is going to have roughly that shape. Now I want the area, or the percent of students between 1200 and 1800. So I drew my bell shape. I centered it at the mean. I centered it at 1500. Now, these types of problems are sort of kicking off a pretty important idea for us. And that important idea for us is that it's often useful to conceptualize area and probability as being the same sort of thing, as being synonymous with one another. And so when I'm asking a question about probability, that's the same as asking for this area under the curve. And that area under the curve, I can think of that as the probability. The proportion of that curve is sort of the proportion of students at the high school, right, that satisfy whatever it is I'm interested in. In this case, that satisfy having an SAT score between 1200 and 1800. So I wrote 1200's to the left of 1500, 1800's to the right of 1500. And then I just broke it down. I said, well, how do these numbers relate to the mean? Well, 1200 is the mean, which is 1500, minus 300, which is a standard deviation. 1800 is the mean, which is 1500, plus a standard deviation, which is 300. So when I'm asking what percent of students or what proportion of the area is between 1200 and 1800, this is the same as asking what percent of students are within one standard deviation of the mean. If we look back at the previous slides, we'll see that our empirical rule tells us that this is 68%. And so, right, just to be clear, there's our answer to the question, 68%. This is a bit of a backwards question. So 95% of the students fall between what scores? Well, here's my picture. So here I started a little bit differently. I know from the empirical rule, so I still drew my little bell-shaped curve. I still centered it at the mean. I still centered it at 1500. Now the empirical rule tells me that 95% is within the mean plus or minus 2 standard deviations. So here I started by writing that out. I said 95% is within the mean plus 2 standard deviations and the mean minus 2 standard deviations. And so at this point, it's just figuring out what that is. Well, the mean's 1500. A standard deviation is 300. So, right, 2 standard deviations is 600. So my upper bound is going to be 1500 plus 600. My lower bound is going to be 1500 minus 600. And so that, as we can see, gives me the answer is 900 to 2100. And so there we are. 95% of all students score between 900 and 2100. All right, question 3. What percent of students score between 1500 and 1800? Well, there it is. That's my picture again. There's the 1800. To sort of make it match into my empirical rule, I included the 1200. Technically, the empirical rule tells me that 68% is within one standard deviation. Based on the picture we already drew for question 1, we know that means that 68% is between 1200 and 1800. However, I'm only interested in the area that I circled there. I'm only interested in the area, the percent of people from 1500 to 1800. By symmetry, remember, symmetry means that those two ends, that those two areas match up, which means that they're the same. So the area to the right of the mean, the area to the right of 1500, is half of the total area, which means that the area that we're interested in, that circled area, is going to be 68% divided by 2, half of 68%, which, if we plug that into a calculator, we get 34%. And there it is, lo behold. All right, this actually might be the last question. What percent of students score less than 1200? So again, 1200, that's where I'm working with. So I started with my initial picture. I circled, in this case, the initial picture. So the initial picture basically tells me that the total area between 1200 and 1800 is 68%. It's a useful springboard for solving this problem, but it's certainly not the answer. It's not what I want. What I want is I want that area that I shaded in with the vertical lines, I want that area to the left of 1200. So how am I going to find that? Well, I know that middle area, the area between 1200 and 1800. I know from the empirical rule that that's 68%. Remember, I also know that the total area is 100%, which means that the area outside of that middle area, the remaining area, the leftover area, is 1 minus 68%, right? It's the whole area removing that 68%. So 1 minus 68% is 32%. So the remaining area is 32%. Now, again, by symmetry, that 32% is evenly split between the rightmost tail, which I didn't color in at all because for this problem I don't care about it, and the leftmost tail, which I colored in with the vertical bars. That is the answer. That is the area that I'm ultimately interested in. So since they both have the same area and their total area is 32%, the area in each tail has to be 16%. Which means that the answer to this question, what percent of students score less than 1200, is 16%. And although the question didn't ask this, it's also true that the percent of students who scored more than 1800 is also 16%.
Lo behold, there it is, 16%. Hot dang, we're good. And so let's stop here. Let's end on a positive high note. Like I encouraged us earlier, make sure, well, I would say actually try to polish off the next PowerPoint. And then once you polish off that next PowerPoint, really sit down and do a lot of practice problems from the textbook. And I think that should hopefully put you in a good place. If you have any trouble, if you have any difficulty with these problems, please reach out to me as immediately as possible so we can either get together and work together on trying to fix these problems, or if nothing else, I can try to kind of hook you up with some of the free tutoring resources that Westchester has available to us. And there we go. Until next time, see you later, alligator.